Hi everyone, I'm Mohammed Faisal, first year PhD student at Boston University. Today I'm presenting TVA, a multi-value computation system for secure and expressive time series analytics. This is a joint work with Zhang, Liagouris, Vasiliki, Kalavri, and Mayank, Varia. Consider a biohealth application where an analyst, a doctor, wants to find the effect of insulin doses during the eating periods of a cohort of patients. The input data consists of multiple time series data input from a glucose monitor, an insulin band, and activity tracker. This is sensitive data that might reveal information about the patient health that we need to protect. Such sensitive data series appears in other applications as well, such as the cluster resource optimization and the energy consumption monitoring. In all of these use cases, we need to compute the evaluation of metrics over time. This can be done using advanced time operators, which we call windows. For example, the tumbling window split time series into fixed size intervals. Session window operators include gap session window and session window. And session windows operators identify periods of activity followed by periods of inactivity. In the gap session window, inactivity means lack of data, while in the threshold session window, inactivity means a value drops below some threshold. To achieve secure and expressive time series analytics, we identify the following requirements. No leakage to protect sensitive data. We also need to support aggregation in specific time intervals, aggregation in windows, and an aggregation on a composition of these operators in order to construct complex query plans. Finally, we need to handle irregular and unordered timestamps because we have multiple distributed data sources emitting data over time over the network. There has been a lot of work in recent years, but unfortunately, none of the existing systems has met all of these requirements. For this reason, we proposed TVA, a multi-party computation system for secure and expressive time series analytics. Consider a set of data owners who agreed to provide the data. Some data analyst was interested in the result of some analytics on the data. So what happened is that data owners send secret shares of their data to some set of computing parties, and the computing parties follow a cryptographic protocol to evaluate the results and share it to the analyst. So for our contribution, we propose the first oblivious algorithms for global and key tumbling and session window assignments on private time series and private time series data. We develop a library of composable operators that can be combined with window operators to construct arbitrary complex plans. TVA provides security guarantees of MPC and can be configured to offer semi-honest and malicious security. We provide an efficient multi-threaded implementation with data flow and protocol agnostic API. TVA's API hides the complexity of MPC from the user. Let's revisit the mobile health analytics application. We have here the question we are trying to answer for this application, and let's see how we can build it using the TVA API. The query is, during each patient is eating period, count the number of insulin doses as they have taken. So let's define a time series with the following scheme. We have timestamp, patient ID, glucose, insulin, and total insulin events. And we can do key aggregation by defining key. So let's do it as follows. Since the query requires aggregation for each user, we key by patient ID. We then apply the threshold window operator in order to create windows using the glucose value with threshold 120. Once we have applied the threshold window, we can now apply aggregation. The aggregation would now have the following keys: patient ID and threshold window ID. Now let's see how this query is being executed. So assume the following table that is secured among the computing parties. The table has following 4 attributes: timestamp, patient ID, glucose, and the insulin. I'm going to hide these 2 columns just to fill up space, and we get the following. Record the threshold window works by the following. It is tracking inactivity according to an attribute falling below some threshold. In our case, this attribute is glucose. So let's visualize this column against time. And we get the following plot. So I'm just plotted these data points here. Now, what we can do is that if we compute the session window naively, we need to perform a full data scan, which would require a number of communication rounds linear to the size of the time series. So instead, we are gonna do the following. We have like two steps protocol. And the first step, we want to identify the beginning of each eating period. In order to do that, in step 1A, we detect whether the glucose value is less than the threshold or not. So therefore, we get the following graph, like points above the line has met the threshold, below it didn't meet it. We know that points above the line belong to some activity window, and what we want to do is to decide which activity window it is. So in step 1B, since we know this information, we initially assign each data point to an arbitrary window and give this window ID of the timestamp it has. So for example, here, for timestamp 7, since it is like a window, I'm going to give it like a window ID 7. And this part requires a constant number of communication rounds. Second step, make sure that the consecutive windows are merged together into one window, and we give this window the smallest window ID. So we do this using our synchronization protocol, which has a butterfly-style data access structure. The idea is to assign each row the previous non-negative ID before reaching a -1, and this requires a log n number of rounds. Now we have specified windows, and we are ready to start analytics in Windows. The gap session window shares also like a similar flow, and you can check the paper for this algorithm and other also algorithms we have introduced. Now let's unhide the answering column in order to evaluate the rest of the application query. Since we now have both window ID and patient ID, we do a key aggregation to evaluate the count. Therefore, the result will be as follows. So we can see here, like we have 1 here. This is the result for the first window, and 0 is the result for the second window. And now let's see how TVA performs. We have done extensive performance evaluation for TVA, and we have discussed multiple metrics such as latency, bandwidth, and monetary cost. To show a practicality of our system, we have also reported runtime numbers for both full end-to-end applications and micro-benchmarking for primitives. We have also reported the speed up of multi-threading and the effect of high delay environments such as WAN. We have implemented queries in both the TVA and Waldo frameworks, and to be able to compare both systems. I'm going to show you only a few highlights. Please check the paper for 4 results. We evaluate TVA with their applications from different domains: energy monitoring, mobile health, and resource scheduling. TVA can execute these queries in online mode. What does this mean? So we have multiple data sources. Each one is emitting some data, and then over different periods, we are doing some analytics. So depending on each application, we have assumed practical input frequency and also a result deadline. For example, like for the energy one, we require that users are emitting data each 10 seconds, and then we have like a window of doing analytics 5 minutes. According to these assumptions, we find that we support online real-time queries with more than 10K houses in the energy consumption and more than 27K patients for the medical study. Note that this is for malicious security and also for WAN setting. According to those numbers, we see that the system is practical for such use case, such a purpose. Now let's see how TVA scales for historical analysis. We run the following experiments to record the runtime of each of the application queries we have. And the 3 applications are the following: is energy for energy consumption, mHealth for medical health applications, and scheduling for the cloud service. We deploy our frameworks in Linux, Ubuntu, R5 8x large, R5 8x large machines, and it is like deployed in a LAN settings, same region. And the experiment are using the malicious security configuration of the system. As we can see here, according to this figure, queries with 4 million input row can be done within 20 minutes. Note that the lines of the mobile health application and the scheduling application has almost the same result because they are using the threshold window and the gap window, which has like similar algorithm, while the energy is like needs a little bit less time. Yeah, so this summarized what I have talked about today. So TVA provides an easy-to-use, secure, high-level time series analytics. It also supports semi-honest and malicious security without information leakage, and it has excellent performance for both online and historical analysis. You can check our code here, and thank you so much.